Okay, so let's recall that if I have a curve C parameterized by the vector function out of t, where out of t has components x of t, y of t, and z of t. T is between a and b. Then the length of C is given by the integral from a to b of the length of r prime of t dt, which is equal to the integral from a to b of square root of derivative of x with respect to t squared plus derivative of y with respect to t squared plus derivative of z with respect to t squared. Now, if I have a curve in the two-dimensional space, then we won't have z of t and we won't have dz dt in the integral formula for the length. And one more thing to point out here is that if I think of out of t as the position vector for a moving bug on the curve, then this integral is giving us the distance traveled by the bug from time a to time b. Okay, so what I want to do now is define the arc length function. So what is the arc length function? So let's say that, again, I have this curve C given by out of t, where t is between a and b. Then the arc length function is the following. So for a fixed t between a and b, the arc length function s evaluated at t is equal to the integral from a to t of the length of r prime of u du, which is equal to integral from a to t of the square root of dx du squared plus dy du squared plus dz du squared. Now, what this is the this integral is giving us the arc length from from a to t. So if this is out of a and this is out of t, then the pink arc length from out of a to out of t along the curve, that is s of t. So s of t is this arc length here. So this is the arc length from a to t. In terms of distance, so if I think of it as the path of a moving object, then s of t is the distance traveled from time a to time t, and notice that s of a would be 0 because it's the integral from a to a, and s of b would be the length of c, because if you look at s of b, then we are integrating from a to b, and if you integrate from a to b the speed function, then you get the length of the entire curve, and so this s of t is what we call the arc length function. Again, s of t is the arc length of the curve, the length of the curve from a to t over the interval from a to t. And now if I take the derivative of s with respect to t, then by the fundamental theorem of calculus, we know we are going to get the integrand evaluated this upper limit t. So by the fundamental theorem of calculus, s prime of t is the length of r prime of t, which is the square root of dx dt squared plus dy dt squared plus dz dt squared. So ds dt is given by this quantity. So as a result, we can say that the differential of s is equal to this quantity multiplied by the differential of t, because ds dt is this quantity. So recall that what this means is that if dt represents a small change in t, then ds represents the induced change in arc length. If I think in terms of distance function, then if dt is a small change in time, then ds is the induced change in distance. And then we can write the arc length formula. That is, we can write the length formula for the curve C in terms of the integral from a to b of ds, where s is the arc length function. So recall that this is the length of the curve C, and the integrand here is exactly the integrand here multiplied by dt here. That's exactly the differential of the arc length function s. So if you remember the formula for the arc length differential ds, then the integral of the integral from a to b of ds would be the length of the curve, from a to b. So okay, so this is the arc length function, and we can express the length of a curve in terms of the differential of the arc length function. Let's do an example. Let's say that I have a curve C where it's given by the vector function out of t, which is equal to cosine ti plus sine tj plus tk, where t is between 0 and 2 pi, and we want to find the arc length function first. So the arc length function s of t would be the integral from 0 to t, and then what do we integrate here? I forgot to write dt here. And so remember that we look at the x component of r of t, and we take the derivative of that with respect to well, instead of t, because we are using t as the upper limit here, let's use u. So let's say r of u. So the first component of r of u would be cosine of u. A derivative of that would be negative sine u, and if I square that, I get sine squared of u. The second component is going to be sine of u, and the derivative of that would be cosine of u, and square that, you get cosine squared of u. And then if I again write r of u, then this would be u, and the derivative of z with respect to u would be 1. Square that, you still get 1. So s of t would be the integral from 0 to t of the square root of sine squared of u plus cosine squared of u plus 1. And I should be writing du here, sorry. And then what we're getting is integral from 0 to t of root of 2 du, and that is equal to root 2 times t. So what we have found is that the arc length function s is equal to root 2 times t. So then we can say that t is equal to s divided by root of 2. So in the vector function out of t, if I replace t by 1 over root 2s, then I get a parameterization of c in terms of the arc length. So I get this. I'm going to denote this. So I'm replacing t by s over root 2. And if I do that, I'm going to get cosine of s over root 2 here, sine of s over root 2, and here I'm going to get s over root 2, and I'm going to call that w of s. So w of s is a parameterization of the curve C in terms of the arc length. So what happens is that, for example, w of s, let me explain that. So let's say okay, so how do I, okay, let me explain explain this a little bit here. So let's say I have the curve here, and it starts at this point, and W of S. So let's say the arc length from here, from the beginning point to here, is S. So S is the arc length from here to here, and then the W of S is this point right here. W of S is this point here. If this is the origin, let's say, then W of S, we can think of that as that position vector, or you can think of that as this point right here. Okay, so W of S is the point on the curve that is at arc length S from the beginning point, which is out of A. Okay, so this is it on the arc length function, and in the next video we will be looking at we will be applying the arc length formula and find the lengths of some other curves.